Good morning and welcome also from my side to the ODRE workshop. I'm Hofer. I will do the first presentation of this session, and the presentation will talk about probabilistic and dynamic scheduling of hard real-time tasks in high-performance computing. I followed this project as a PhD student, visiting University of California, Berkeley, and together with Siemens Corporation. So how did I get the idea for this project? In Industry 4.0, we have architectures that deal with system of systems and interaction of various systems. And I tried to find, or still try to find, an architectural model that is safe and generic and that makes the system more reliable, reduces security threats, but is still applicable in multiple contexts and technologies. But very soon, by doing a mapping study and looking after the research that has been done so far, I figured out that I have to deal with a bigger scope. My project has to deal with three paths because while we're just dealing with one bigger system, that is this conglomerate of cyber-physical systems, all heterogeneous, all linked together, which we can describe as a major architecture. At the same time, I will have to deal with traditional aspects of this new form because there will always be embedded controls that have been working as legacy for long years on the systems installed, and they will still be employed in this new Industry 4.0 systems as we figured that it is hard to exclude a legacy system that is still working. And at the same time, we will also want to include embedded systems that are on-site, on-device, and do specific tasks. So that's the second part. But the third part that will be stronger and stronger is the virtualization. Virtualization intended as edge computing, where we will have diagnosis and health monitoring, but also virtualization intended as virtualization of control. So when you start moving the control application from on-site, on the device, to an edge computing infrastructure, to a bare metal infrastructure that is close to the production process or to the actual plant, then you might use virtualization to improve and optimize the cost while still wanting to also make the things more manageable, make the operation and the maintenance easier, a thing that comes along with containerization. So in this part of the probabilistic scheduling, we talk about how can we put multiple containers on shared resources but still keep the determinism and real-time constraints, and all of this while using off-the-shelf technology. So what we wanted to do first then is evaluate how the actual off-the-shelf technology of today works in latency. So what's the actual system latency? Then how by statically scheduling the resources on shared containers on these resources we have on these virtual systems, how this impacts the determinism of the systems themselves, of the tasks, the deadlines, and finally, how if one of the resources goes in overload, like say a task takes longer than needed, so it would shift all the other tasks by execution time, making them probably miss their deadlines. So how can we manage that and reschedule the resources in a way that they can still meet their deadlines by using other cores, other shared system resources. At this point of research, we are at the last step of this investigation, trying to figure out how to process this dynamic scheduling. So what we want to know now is how we can use this dynamic approach on off-the-shelf technology and how we can now combine probabilities and predict that we have to reschedule our system, that we have to reschedule tasks, and thus increase the stability and reliability of a virtualized system as well. Keeping architecture in mind, we have the following situation. Instead of having a single container, a single resource for each task that has to run, we try to stack them together and allocate shared resources, but it could bring some problems with it, as you probably imagine. Let's say you have this real-time system where you have a conveyor belt and cameras that check through imaging, taking 8 pictures per second, check the quality of the product. Then you have containers, Docker containers in this case, that process the image and try to evaluate if the product is conforming to the quality standards. What could happen is that instead of having one camera allocated to one container, which then runs on its dedicated CPU and allocated resources, if you share them, the combined execution time could actually be longer than expected. Let's say, for instance, a product image changes a lot, and we know that the content of the image often determines the duration of the computation. It could cause that the first execution, so the first camera, like here in the example, takes longer than expected to elaborate the image, which then would push forward in time the execution time of the second picture, which would miss the deadline, and thus we would lose the opportunity to actually discard the product from the belt. So our solution to that is we want to try to use standard off-the-shelf technology as said, and experimental evaluation mostly. So we take theoretical concepts and try to experimentally evaluate their qualities. Then we would like to use mature software and kernels, so we don't want to use anything that is research or experimental as a software, so it could be used right away by industry. And flexible containerization techniques, because the demands nowadays are high, as we know. All together with management through orchestration. So an orchestration tool that manages these resources in a proper way. While it all has to, of course, run on different systems. We want to make it run on a cloud system, on a edge computing, on a bare metal system, no matter what. How do we do that? So far we heard that we did latency tests on the cores to determine if we can do this migration, if the systems are sustainable, if the virtualization is viable of control systems, and we applied that to the 3 different machine types, virtualized and bare metal. And true virtualized systems are either generic or compute intensive, so with more hardware access. We tried it on different containerization techniques, finally figuring out which one is the best. And we also tried it with different operating systems and real-time patches, finally figuring out that the best combinations is Ubuntu for its maintainability with real-time Linux, so Preemptor T or Xenomite patches, respectively. We performed the latency tests and saw that the actual mean is low enough, so we talk about a range of 10 microseconds. And we get the best results considering the scaling, because Xenomite has scaling issues beyond 4 cores, as the community says. They're the best results, and that latency test we had with the long-term support version, maintainability again, and Preemptor T for the real-time preemption. Docker as the more featured version of Balena, which is more focused on Moby container software, which is more focused on small IoT devices. While for the second step, we wanted to find the determinism if we start scheduling actual tasks on these resources. So considering, for example, this situation, the actual computation time of each task that we schedule is determined by the firing latency and the runtime, complete runtime taken for this task, which can then be split into, as we see here, call it firing plus the system noise and the actual delays that are caused by the tasks, which here is NIK, which could be, for example, I/O delays because of memory you had to fetch from the disk or cache, and the computation itself, which is TI. And but in this second test, we analyzed the first two parts by using simple computation-only tasks. So the task itself does no I/O, and thus all the latency and delay we measure is other system tasks and the scheduling that occurs. The results show that the distribution of our runtimes is actually very close to normal, which is a good result because it gives us better ways to compute the total distribution, the total probability. While if we take smaller and smaller tasks, so instead of having 10 millisecond tasks, if we take the same tests with smaller tasks in 900 microseconds range, then we see more the influence of the system latency, which you can see here, peaks, variations, it could be interrupts or task switching, and also on the main distribution itself, you see the influence of it. And in this third part, we want to start now manage these delays that could cause actual problems in maintaining the deadlines. And we do this through this orchestration, as said, by 3 steps. We configure the environment, the division of resources, we monitor the task and its performance, each one of them, and then we predict and trigger change. All of this giving us data about the system, about the distribution, and how to react and reschedule things. For the monitoring, in this test, we will first start again with the computation only. Then we will include I/O, memory bandwidth, and other things that are connected to typical tasks. And then we will try complete use cases by replicating scenarios where you have continuous interaction with the system. And this should give us then, in every case, the overview of probability of failure of all the tasks that are running on a system. We have to respect the deadlines for this and also stay consistent with stress. In summary, we have shown that viability of virtualized control applications is confirmed, and we can do this migration from on-site control into a virtualized environment. And as a work in progress, we foresee to test multiple dynamic scheduling algorithms, to test them in simulation, and also for use cases to see how the performance of this orchestration system is. Another future work that I will do as part of my PhD to conclude it is to see what are the threats, how the security perspective changes if I move control applications from an embedded device into a shared virtualized environment. What are the implications? And with this, I conclude my talk, and I'm now open to questions.